Welcome to the second lesson in our 7th unit on vectors in geometry. Today we're looking at adding and subtracting vectors, and our goal here is just to be able to add and subtract vectors using a variety of methods. We're going to focus mostly on just the joining tail to head method. There are other methods, but given our time frame for this course, we'll focus on the one method only here. We're looking for the resultant vector when we're adding and subtracting vectors. A resultant vector is just a single vector that represents the combined effect of two or more other vectors. It's the result, hence the name resultant, the result of the sum of the vectors. So if we're just having vector u added to vector v, for example, we often will use the lowercase letter r with our vector symbol above it. So our vector r, the resultant vector, could be equal to the sum of maybe two vectors, vector u plus vector v. Okay? To add vectors together, geometrically what we do is we join the vectors together tail to head. All right? And the order of adding does not matter. So, for example, if I have that u plus vector v, that is exactly the same as taking vector v and adding to it vector u. Okay, so the order is commutative. You can do it in either way and get the same answer. The resultant is the vector created by joining the tail of the first vector to the head of the last vector. So let's take a look at what this would look like geometrically with pictures of vectors. Let's say we had vector u heading horizontally in the direction of the right. So I'll label that vector u. Let's say I had a small vector v heading upwards. So I'll label that vector v. That's vector v there. If I wanted to add u and v together, I would take my vector u. So I've got u. I'm going to put an add sign here, plus vector v. I'm going to take my vector u, draw that in. There's my vector u. I'm going to join up at the head of vector u. I'm going to join to that the tail of vector v, or w. It almost looks like I wrote w there instead of v. So now I've done what step one in this instruction here. I've joined my vectors together tail to head. My resultant vector, so right here, the resultant vector is the vector created by joining the tail of the first, so I'm looking at the tail of vector u, to the head of our last vector. So I only had two vectors in this case. I want to join that tail of vector u to the head of vector v. So my red vector I've drawn in here is my resultant vector. Okay, that represents my u plus v. If I would have added these in the opposite order, just to show you the v plus the u, I would start with my vector v. So it's going to go up. There's my vector v. If I add to it vector u, I'm going to put the tail of vector u on the head of vector v, and I get this one. So there's my vector u. My resultant vector is going to look like this. Okay, so if I've done this with any degree of accuracy here, you can see that my two red vectors that I've drawn are going the same direction and have the same magnitude. So it doesn't matter what order I add in. It is commutative. It can go either way. Now, vectors are used a lot for forces, so we're going to be doing some examples as time goes on using actual life examples, and forces are vector measurements. So I'm going to put some things in here. A force is just a push or a pull that tends to move an object. For example, I'm going to say 10 because I could apply a ton of force to try and push my car, but I'm just not strong enough to overcome all the other forces that are keeping it from moving. Okay, I'm not strong enough to overcome the force of friction and the force of gravity that's keeping that car sitting in one spot. So it tends to move an object. I can apply that force, but it might not move the object if it's not a force great enough to overcome all the other forces that are acting on the object. Forces have magnitude and direction. So when I push on the car, I've got my actual Newton force I'm pushing with, but I also have the direction. Am I pushing it forward? Am I pushing off to the side? There is a direction there, so it is a vector. And again, forces are measured in newtons. They're their units there. So I'm just going to summarize that here under force. Okay, so I've summarized that with a push or pull that tends to move the object. It doesn't have to, but it usually does if there's enough magnitude behind it. It will have magnitude and direction, making it a vector. Often when we write our letters for forces, we use R for resultant. We often use letter F for forces. So if you see like an F with our arrow on top, that's just representing our force. If we have multiple forces, sometimes we use subscripts. So we might have force 1 and force 2. They combine together. So a couple of different forces, we might then get a resultant out of that. So those are things that we use. And magnitudes of forces is measured in newtons, and that's to pay tribute to, of course, Sir Isaac Newton for all his work in physics. Examples of adding vectors. So what I have here, this little box here, this little square, that's to represent some kind of an object. Okay, there's an object there. We have somebody trying to applying 10 newtons of force forward or to the right. And we have another thing applying a force of 20 newtons to the right. So you can see that my 10 newton vector is half the size of my 20 newton vectors. Remember, when we draw them, we should be trying to make them representative of the actual magnitude to some degree. Now, both of these are going in the same direction. So when those two people are maybe pushing on that object, applying that Newton force, they're acting in the same direction. So we really are combining those. If I think of my whole concept of adding those vectors together, I've got my 10 Newton force heading forward. So there's my tail of the first, and to that head of the first, I'm going to put the tail of the last. I'm going to put my 20 Newton force. My resultant force then would go from the tail of the first to the head of the last. Now I just wrote it underneath so that you could actually see it. Technically it would go on top of it, but I didn't want it to get too confusing. So altogether, this one's pretty easy. The resultant here is going to be 30 newtons because it's just 10 plus 20, 30 newtons, and it's heading to the right as well, just like the other two are, because we're not changing direction at all. It's just still going to the right or going forward. Okay, looking at example B here, again, we've got the box in the middle. This time the two people are not pulling in the same direction. They're pulling in opposite directions. So the 10 Newton force is heading to the left. The 15 Newton force is heading to the right. So if I were to capture this one, I've got my 15 Newton force heading to the right. But then my 10 Newton force is coming back against it. Okay, so if I look at the tail of the first to the head of the last, tail of the first to the head of the last, there is my resultant vector. Okay, so what we have happening here is we've moved to the right 15, but we're moving back 10 collectively. If we think about that, we end up with a resultant of 5 newtons. It's still going to go to the right, but only because it's outpowering the 10 Newton force by 5 extra newtons. Okay, so that would be the case where they're going opposite directions to each other. Part C is a little bit more interesting. So this is meant to be a 90-degree angle in here. One is going to the right and one is pulling down. So if I look at adding those together, I've got my 15 Newton force here, 15 newtons here, and then my 5 newtons is pulling down. Okay, I've enlarged that just a little bit so we can work a little easier with it. So again, I drew my first vector, I joined the second vector to the head of the first, and then my resultant goes from the tail of the first to the head of the last. So this is my resultant vector. Now I need to get a magnitude here. Now these do apply at a 90-degree angle, so it makes a nice little right angle triangle. We have our friend Pythagorean theorem that we can use here to calculate that magnitude. And remember yesterday we talked about, or in the previous lesson, we talked about the absolute symbols, the absolute value symbols, those bars on either side indicates magnitude. So the magnitude of my resultant is going to equal 15 squared plus 5 squared. That's just our Pythagorean theorem. We get 225 plus 25. That's going to give us 250. Our resultant will be the square root, the magnitude of the resultant will be the square root of 250, which when we put that in our calculator, it comes out to about 15.8 newtons. Okay, so it's going to have the same units, it's 15.8. Now, the other thing we need is direction for this. So our direction, what I'm going to do is calculate this angle between the resultant and the 15 Newton vector. And because I've got a right triangle, I can use my SOHCAHTOA. So this makes it a nice opposite and adjacent. So tan works wonderfully for this one. Tan of theta is going to equal 5 over 15. So my theta will be the inverse function of tan on that 5 over 15. Those are supposed to be curved brackets there. So if you put that into your calculator, make sure you're in degree mode, that's going to give you approximately 18.4 as our angle. So my conclusion would be that, therefore, the resultant, so these ones are a little bit trickier in terms of how we write it. It's not just left or right or up or down. The resultant is 15.8 newtons acting at an angle of 18 degrees, roughly, I'm just rounding that, to the 15 Newton vector. Or if I had that labeled as force 1 or force 2 or something like that, I could say that instead. But just to be clear, to the 15 Newton vector, period. There we are. All right, now we just need to learn how to subtract vectors, which, because we know how to add, subtracting is super easy. Easy in that it's just like integers. To subtract vectors, we just add the opposite. So let's say we wanted to, let me just write that in, we add the opposite vector. And we talked yesterday, or in the previous lesson, about what opposite vectors look like. We add the opposite vector. So just like with integers, when we learned how to subtract integers, if we had u, vector u, minus vector v, we could rewrite that as vector u add, so like our integer rules, add negative vector v. Okay, and negative vector v we know is the opposite. So all we do, if we had u looking like, let me draw a vector in here, let's pretend this is vector u, and let's pretend this is vector v, heading up like that. What I'm going to do is not join those head to tail, because that would be adding them. If I want to subtract them, I'm going to take v and just make it go the opposite direction. I'm going to try and draw V, the same magnitude, but the arrow on the opposite end. So that one is now negative V. And so when I add this together, I'm going to take and pick that up, add it still head to tail. So there's my negative V. And then my resultant vector is still the tail of the first to the head of the last. So there's my resultant vector. So it's just adding, it's just you have to remember to turn the whatever you're subtracting into the opposite direction. Okay, we're going to do some examples on our next video.